Okay, for this lesson, we will continue to discuss on some example of DC bias analysis of BJT bias circuit. So before we go to the examples, let's do some revision. So the first, this is the basic knowledge that I want all of you to remember this. So first of all, for the symbol of the BJT. So BJT, you know, we have the NPN and PNP. So usually we will focus on, basically we will focus on NPN. So the symbol is okay. So the symbol will be something like this. So we have three terminals. Okay, and then the middle terminal is, we call it base, and the terminal with the arrow here, we have arrow here, is emitter, and then we have collector. Okay, so this is the symbol. Okay, if we have the PNP, what is the symbol? The symbol is almost the same symbol with the NPN, but the difference is the arrow direction. Okay, the difference is the arrow direction. So this is PNP. So PNP also, the middle one is base, and then we have the terminal with the arrow is emitter, and this is collector. Okay, so next we have symbol, terminal. How about the current? So every terminal will have their own current. So base will have base current, emitter current, collector is collector current. So for the NPN, the base direction will be pointing in. So this is IB, and then the emitter will follow the arrow direction, which is towards downwards. This is IE, and then collector will pointing down. This is IC. So you can see the IB is pointing in of the BJT, collector also pointing in, but the emitter current exiting the BJT. So we have here the KCL is IE equal to IB plus IC. Okay, so this is the current relationship between the three terminals. Okay, if you consider the PNP, so this KCL, relationship between the currents inside the BJT is similar. So we have the emitter will be divided into two parts, which is the base collector and then the base current and then collector current. So first of all, you know, the emitter will be the direction will be will follow the arrow direction of the symbol. So the emitter will be facing or towards the upward. So this is IE. Okay, now you see this is the emitter current is entering the BJT of PNP BJT. So the base collector will be exiting. So the collector IC here, and then the base here, this is IB. Okay, so note that the difference between the NPN and PNP. I think maybe in the previous class I did not emphasize on this PNP, but you need to know how the difference between PNP and NPN in terms of the current direction. Okay, but in terms of the current relationship is the same, which is IE is equal to IB plus IC. Okay, and then we also have another parameters. We have beta. Okay, beta is IC over IB. So this is beta. Okay, when you have the beta, you can have the relationship between IC and IB. IC is equal to beta IB. Okay, and then you have also IE. What is the IE? IE is beta plus 1 IB. Okay, so this is we have discussed this one. Okay, and then this is current relationship. And then another point that you need to understand is you see here we have base collector and emitter. We have 3 terminals. Across the terminal, between the terminal, there will be a voltage drop, because this is when I say between 2 terminals, actually this is referring to the between one junction, PN junction. Okay, so from base to emitter, we have what we call it VBE, voltage base to emitter, and then between collector and emitter, we have VCE. We have VCE, and then between collector and base, we have VCB. Okay, if you draw the NPN structure, okay, and this one is collector, base, and emitter. So the VBE is actually the voltage at the base, at the P type, with respect to the N type. Sorry, this is N type. With respect to the N type emitter. Okay. So why this is important? Because we want to relate with the operating region of the BJT. Okay. When the BJT operate in the as an amplifier, okay, the BJT need to be biased, or need to be the location of the operating point need to be in active operating region. So the active operating region is where we bias heat. The base emitter junction need to be forward bias, and collector base junction need to be reverse bias. Okay, so you know here when we assume the BJT in active operating region, we will consider the base emitter junction in forward bias. So we will consider the VBE is equal to 0.7, because the PN junction in a forward bias can be modeled or can be represented by a DC battery source equal to 0.7 volt. So this is another basic information that you need to remember. Okay, so in the previous class we have discussed, we have learned about how we can do the DC analysis. Okay, this is the general step, or this is the recommended step for you to do the DC analysis. Okay, the first step is you replace the capacitor with open circuit, because in the amplifier circuit usually we have the connection to the AC input source and connection to the load. So this connection is done by using the DC capacitor. So we call it capacitor coupling. So when you do the DC analysis, this capacitor need to be replaced with open circuit, and you need to remove the source and the load. Okay, this is the first step. Okay, and then the second step is you identify the DC bias circuit. If the DC bias circuit is voltage divider bias circuit configuration, so you need to apply Thevenin transformation. The Thevenin transformation is applied at the resistor network connected to the base. Okay, so at step 3, you write the KVL along the base emitter current pass. Okay, So when you write the KVL at the base emitter current path, you assume the base emitter junction in forward bias, so VBE is equal to 0.7. And then when you do the KVL, there will be base current and there will be emitter current. So the emitter current can be represented by the base current using this equation. Okay, now you should have a KVL equation with only IB as the parameter, as the variable. So you can solve the IB. So once you got the value of IB, you can get the IC by using the beta. Okay, this equation. And then another thing that you can do is you can also get the value of IE. So IE is equal to IC plus IB. Okay, so number 4. Okay, ada step 3, you already get the current values. So at step 4, you want to solve VCE. So to solve the VCE, you need to write the KVL along the collector emitter current path. Okay, so let's do the example number 1. So this is for the question is for a BJT amplifier circuit shown in figure C2. Given beta is 150, and then we have VBE is 0.7. Okay, and then we have VT and we have VA. So VT and VA is not relevant for now in our DC analysis. So for now we can ignore these two values. Okay, the question is show that ICQ is equal to 2.1 milliampere and VCEQ is equal to 5.3 volt. Okay, so how we can do that is, okay, the first step is remove the capacitor. So we will remove the capacitor, open circuit. So this part, the AC input source will be disappear. We also remove this capacitor C2, so the load can also be ignored. You can ignore the load. Okay, now you have the bias circuit only. And then the second step is Thevenin. So why you need to do the Thevenin? Because this bias circuit is a voltage divider configuration. So you need to simplify the resistor network connected to the base. So this is base. So the resistor network connected to base. Okay, for Thevenin, you need to calculate two parameters. One is the R Thevenin. So R Thevenin is the parallel of R1 parallel with R2. So this is 15K parallel with 4.7K. So this is equal to 15K times 4.5K over 15K plus 4.7K. Okay, so we can calculate this one. So you can get okay, the calculation is 15 times 4.7 divided by 19.7. So you got here is 3.58 kilo ohm. Okay, and then next parameters is V Thevenin. V Thevenin is the voltage at this point. So voltage at this point. So this is using the voltage divider. This is 4.7K over 4.7K plus 15K times 12. So the answer here is 4.7 divided by 19.7 times 12. So we get 2.86. So 2.86 volt. So once you got this equation, you can redraw your circuit. So you can redraw your circuit. At the base connection, you will have the V Thevenin 2.86 volt, and then you also have the R Thevenin. This is 3.58 kilo ohm, connected to the base, and then at the emitter side there is no change, so we have RE is 1 kilo ohm, and then we have RC is 2.2 kilo ohm. So at the RC, the VCC is 12 volt. So this is the redraw, this is the simplified circuit. Okay, and the third step is you need to do the KVL at the base emitter junction. So base emitter junction, basically this is the base emitter junction. So this is the loop, the input loop. Okay, so the KVL will be minus 2.86 and then plus. Okay, here I suggest you to draw the current direction. So the base is inside, and then we have emitter here. Okay, so 2.86 plus, and then the current at this Thevenin resistor is IB times 3.58K, and then we have VBE is 0.7, and then we have the voltage drop at 1K. 1K is IE times 1 kilo ohm, but IE can be related to the base current by beta plus 1 IB. So beta is 150, so we have 151 IB 1K equal to 0. You got here 2.86 plus IB plus 151 kilo IB equal to 0. Then you can get this one, IB is equal to 2.86 minus 0.7 over 3.58K plus 151K. So this is the equation to get the IB. So we got the IB 2.86 minus 0.7. Okay, 2.16 divided by 154.58. So you got here is 0.01. Let's say I round it. This is 14 milliampere. Okay. When you get the IB, you can get the IC. IC is 0.014 milli times beta 150. So times 150, we got 2.1 milliampere. And then IE also you can calculate. IE is IB plus IC. So this is IE is equal to 2.114 milliampere. Okay. So the next step is you do the KVL at the collector emitter loop or collector emitter current path. So the KVL is minus 12 plus IC times 2.2K. The current at the 2.2 kilo ohm is collector current. So this is 2.1 milli times 2.2K. And then now we have between collector and emitter, we have the voltage VCE. So this is the VCE. And then we have the voltage drop at 1 kilo ohm is IE times 1 kilo ohm. So IE is 2.114 milli times 1K. So this is equal to 0. So you calculate all the each of the term. So 2.1 times 2.2, 4.62. And then you have this VCE, and this is 2.114 equal to 0. So VCE, you got 12 minus 4.62 and minus 2.114. So you got 5.3 something. Okay, so this is our calculation. Okay, so you can this is calculation here. Okay, you can compare to the question. The question is show that ICQ is 2.1 milliampere and VCEQ is 5.3. So our calculated value show is consistent with the value stated in the question. Okay, so this is the answer.